Before we begin to look at ECGs in detail, we need to first look at how the heart functions to keep blood pumping around our body. That is, after all, its main purpose in life. To start with, let's draw how the heart sits in place within the chest. We can see that the heart lies within the midline of the chest, with its apex pointing to the left-hand side. If we open up the heart, we can see that it's actually made up of 4 separate chambers: the right atrium, the left atrium, the right ventricle, and the left ventricle. Each chamber contains slightly different structural features, depending on what its intended function is. If you're using your workbook, you'll find the answers to some of the questions in this video and some of the other answers in the web pages that we've linked. Here, we're going to focus mainly on the part of the heart that's most important for ECG interpretation, the electrical conducting system. This is the network of conducting fibers that work together to create the heart's natural contracting rhythm. Each specific part of the conducting system transmits the electrical signals at a different rate. The slowest possible way that electrical signals can travel through the heart is via myocyte to myocyte junctions. This isn't a good way for the signals to travel because it would be too slow to produce an organized and synchronized contraction. Instead, the electrical conducting system provides a much more efficient highway for the electrical signals to travel down. If we take away the background, we can see the different components of the conducting system more clearly. The pacemaker signal originates from up here in the sinoatrial node. This is the natural pacemaker of the heart, and it usually depolarizes between 60 and 100 times per minute at rest. It's important to know that any cell within the heart can actually act as a pacemaker, but the cells of the SAN are special in that they depolarize spontaneously. There are other cells in the heart that can depolarize spontaneously, but the SAN does this more quickly than any of the others. Hence, it will usually set the rate of the heartbeat. The signals then spread through the internodal pathways, causing contraction of the atria and forcing blood into the ventricles. The electrical activity is spread from the right atrium to the left via Bachmann's bundle. This allows both atria to depolarize and contract simultaneously, keeping them in sync. But there's a problem. These conducting fibers spread the depolarization so quickly that, if left unchecked, the ventricles would be activated before the atria have finished contracting. Well, in order to fix this, the heart has its own delay mechanism built into the pathway. This delay mechanism is called the atrioventricular, or AV node. The conduction through the AV node is much slower than through the rest of the heart, and it's this that allows the atria to fully empty before the ventricles contract. Now that blood has made it into the ventricles, the depolarization wave reaches the bundle of His fibers, which then divides into left and right bundle branches. Each of these supply one ventricle respectively. The left bundle branch then splits again into an anterior and posterior fascicle. This happens because the left ventricle is much larger than the right, and so to maintain synchrony, a second bundle helps to spread out the electrical activity much more quickly. All of the bundles eventually terminate in small Purkinje fibers, which help evenly distribute the depolarization wave through the cells. In the next few chapters, we'll need to use this knowledge of anatomy to help us understand the different waveforms on the ECG and how these might change when different pathologies start to affect the heart. For now, though, you should fill in the pages of Section 1 in your workbook, and we'll see you in the next video.